I've spent these past couple videos hooking up high voltage transformers and everything else, and what I haven't done is talk about one of my favorite safety devices in the electrical world, which is the ground fault circuit interrupter. If you're across the sea, it'll be called an RCD. Here in the States, we call it a ground fault circuit interrupter. If you have a bathroom with a push button on your outlet that resets, you've encountered a GFCI. I want to talk about what that does. It's pretty cool. So I've got a test set up here, and we'll explain what we're going to try to do. So here in front of me, I have a brand new GFCI, and I want to talk about what a GFCI does. So in any electrical circuit, you've got the equivalent of supply and return. Something goes in, it must come back out. What the job of this device is to detect leakage from that return path. So if I have 20 amps come out of this side, 20 amps should go back in the other side. Probably should choose a lower number considering this type of outlet. How about we have 1 amp come out, and it goes out of the outlet. If it only gets back 0.7 amps, you know there was leakage, right? So what this circuit is doing is it's comparing what's leaving versus what's coming in. Now, it doesn't really have to go back through the third hole. It doesn't have to go out through the ground. It can be leaked off to ground somewhere else. Whatever happened, a different path was taken, and energy leaked out of the circuit and did not all make it back in. Probably one of the best safety devices we have. Pull my other document here. Hold on one second. I printed this from asc.ohiostate.edu. I actually have one of the best little diagrams. I'll flip this page over here in a second, but this is a very good description. It's very succinct, right? So any amount of current over 10 milliamps, 0.01 amp, is capable of producing painful to severe shock. Currents between 100 to 200 milliamp, 0.1, 0.2 amp are lethal. They're not lethal why you might think. A lot of people will think, well, I get shocked, and what's going to happen is my heart stops. Your heart doesn't stop. It goes into, we call fibrillation. It's just shaking. It's no longer beating properly. And if you don't have somebody who can administer CPR, you're dead. Or have an AED nearby. So the big problem is if you're working with electrical systems, you need to be aware of the danger, and especially across the chest. If you are holding something, you reach into a circuit, like let's say pretend this was grounded and there's a live wire next to my hand. If I touch here and here, electricity will want to take the least path of resistance. It will want to go through my hand. This isn't always going to save your butt, but it's a good point to make. So if I touch this and I touch something that's electrically conductive and this is grounded, the energy will try to go through my hand. So oftentimes when working with currents, you'll try to keep one hand in a pocket or use one hand near something that could be potentially live. It's not what you should do. You shouldn't go work on live circuits. Just wanton. You should be very careful what you do regardless. But if that energy goes across your chest, it can bruise you, it can leave scarring, and it can kill you. So if you talk to anybody who's been an electrician for any number of years and worked on higher voltages above 120, like 277 or 480, any of those guys who've ever been shocked might even have a scar across the chest to show if they've lived to tell the story. So, very basic thing here. So right here, we have a nice chart. That's really why I wanted to print this. And I'll put the webpage link on the description of the video. But threshold of sensation is down here. 0.001 amp, right? So that's 1 milliamp. You can barely feel it right there. This is mild sensation at 0.01 amp. So 0.01, that's 10 milliamp. So I want you to think about the fact that when do you think a GFCI fires? Because right here we get to severe shock, painful shock, can't let go, right? Going all the way up to 0.1. It doesn't take much. Death between 0.1 and 0.2, severe burns, breathing stops up to 1 amp. It doesn't take much. A GFCI will trip generally around 6 milliamp. Generally. It's different between vendors. So instead of 0.001 right here, it's going to be 0.006. So somewhere right in here. That's where the GFCI trips. So this little device, 20 to 30 bucks. The reason we mandate these to be installed in garages, in outdoor fixtures, in kitchens, in basements, anywhere where an outlet could go on an extension cord outdoors or with a power tool. You know, a lot of power tools now are double insulated, but that's a newer thing. Anywhere people could potentially be exposed to a shock. I didn't mention bathrooms. We should mention bathrooms, but anything where you have a device that would be exposed to water or moisture, where potentially conductors could reach human skin. Because guess what? We're a bag of salt water. We're pretty damn conductive. So what this device does is it cuts off power right there before you get anywhere close to death. Way down here. Also why you should test these things. They can go bad. I've got a video where one actually got water and it was sitting there faulting out and dies. So I don't think people talk about how great these are as an invention. I'm sure countless lives have been saved by this, and there are no metrics kept on that because nobody's going to call and be like, oh, my life was just saved by a GFCI. And the best part is, let's say you're on a construction site and you don't know if your power is on a GFCI. It darn well should be. Guess what? They're portable. If I can impress anything on you, it's that your body is very salty, very, very conductive, and this guy will trip a circuit right about there before you get anywhere up to the bad stuff. So, set up. I'm wiring up this GFCI for the demo, and I had just recently made fun of non-freedom countries, i.e. non-American countries, for the goofy color code of their power cabling. And the computer power cord I happen to chop up to do this uses those wonderfully weird colors of brown for hot, neutral is blue, and ground is green with a yellow stripe. You guys are weird. You guys are so weird. Alright, so here's our GFCI test circuit, and it does look like a mess, but I'll explain. So we're at 120 volts, there's this nice lamp here, and what I've got is, I used our dim bulb tester. Dim bulb tester, as somebody called it earlier, but basically that light is in series with our wire here. So the circuit is running through this loop. I've connected the ground to the hot lead. Right, so there's a leak of 0.1 amps. And if I move my papers over here, I've got my pile of papers. I apologize, let me get this out of the way. What's lethal, guys? What's lethal? Is that lethal? 0.1 amp? Huh? That's death, right? 0.18. You'll be dead. There's enough current going through this meter to kill you in leakage right now. And I've got this going straight in right now. I'm going to connect this GFCI and I'm going to click it on, and I want you to watch how quickly the interrupter works. I'm going to turn the lights off for full effect for this. Now I want you to pay attention. There's going to be an LED light and you're going to hear a clack. I'm going to flip the power switch first. Ready? That was it. It just tripped. Current was interrupted so quickly, still live, that interrupted current so quickly, you saw the bulb go like that real quick, and it cut the circuit. There's nothing going on here. This is just noise. That 0.21 you see popping up is electrical noise from the room. No current going through, right? So this is how quickly that device could save your life. Okay, so current is so small. I have trouble reading it. I don't know why I didn't think about this, but it's parallel resistance, so I can't obviously use a kilo ohm resistor here. It's not. I'm not doing this in series. So to make this easier, and I don't have a meter that'll read this low of a current, but if somebody does, I should repeat this because it'd be interesting to test different brands. So I've got a 300 ohm potentiometer here, and you can see we're not really putting any current through it. The light bulb is lit. We are going through the GFCI. So what's happening is power is going from the GFCI to the light bulb over here, and then from the light bulb, it's coming over to here. It's going through here. It's going back in. And it's going to the neutral, and then it's heading back into the variac. Where we've created the leak is here. We've tapped on the hot line. Ignore the colors, but we've tapped on this hot loop that's going through, and we're going through our current meter, through the potentiometer, and off to ground. So let me, my color's mixed up here. Sorry, that's going through potentiometer. Potentiometer goes through current meter goes to ground. Yes. So I'm staring through the camera looking at this. So I'm gonna start increasing or decreasing the resistance on this, because right now we're at a full 300 ohms. I'm gonna slowly turn this down, and if you watch, Mr. Lightbulb is gonna die slowly. Oh, before I do this all the way, let's set this to max. Here, I need to clear that. It's getting noise from the room, which I have to apologize for. There's a ghost of 0.22, so that is obviously not accurate. You can ignore that, but here we go. Turning the knob slowly. There we go. At 0.04, and if that's the case, go over to here. 0.04 is going to be in here where you're going to feel the shock and not be comfortable, but not be dead. So that's less ideal. I don't know that this meter is good for this type of current check, but 0.04 is when it claims it saw a peak of. Physiologically, I don't know what that's going to do to you, but the point here is, being someone who's been shocked before and had GFCIs fail from bad tool installation and other stuff, these are really a lifesaver. If I try to re-enable the circuit right now, it won't let me. So if you ever have a GFCI in this state, and I don't really have a way to insulated to grab that and reset it because it's extremely firm to push that button in, you'd see it would immediately fault back out. If you're ever in a situation where you're trying to reset a GFCI and it keeps faulting, you should stop, because something downline from that GFCI that it's protecting, or an extension cord plugged into it, something is still shorted. And yeah, let me go back here real quick. So what have I hope you learned today? What's the takeaway you should take away from this monstrosity sitting on a bench is GFCI save lives. If there's one device that somebody should have won a Nobel Prize for, it's the GFCI. This little unsung hero lives in your wall waiting for you to have a tool or something broken and protects you from absolute terrifying death. So, pretty cool little piece of hardware. No one thinks about it. I don't hear anybody talking about how thankful they are for it, but it's a wonderful thing. So, next time you look at your wall, say thank you to the little box keeping you alive.